Now welcome to the new video on API 577. This is probably going to be the last video for API 577 series for welding and metallurgy. In section 10, which is the previous video, we have already seen that what are some metallurgical aspects of welding. So we have said that the welding should have desired amount of strength, it should have desired amount of ductility so that it can bend. It should have the required amount of hardness. There were also restrictions on how much hardness is possible in certain kinds of material. So all of those things we have seen in section 10. Now we'll move towards section 11, that is refinery and petrochemical plant welding issues. So in general, this section provides the detail for specific welding issues encountered by the inspector in refineries, petrochemical plant. This section will be expanded as more reflected by industry experience that are added. So the first issue that we are going to talk about is hot tapping. We have already talked about what is hot tapping, and when we are talking about the main code, that is all the requirement for hot tapping are given in all of the codes, that is 510, 570 and 653. So we have seen what is hot tapping. Hot tapping is basically making a cutout for a nozzle while the piping is in service. So hot tapping requirements are generally given in API 2201. Those are recommendations to be followed whenever the hot tapping operation is done. So API 2201 provides an in-depth review of safety aspects to be considered when hot tapping or welding on an in-service piping or equipment. Because you understand this, if the hot tapping is done, if the fluid that is flowing inside the pipe is very flammable, then the hot tapping can lead to flames or it can lead to combustion of the fluid, which can be very detrimental. Prior to performing this work, a detailed written plan should be developed and reviewed, and the following is a brief summary of the welding related issues. Two primary concerns with welding on in-service piping and equipment are burn through and cracking. Burn through will occur if the unmelted area beneath the weld pool can no longer contain the pressure within the pipe or the equipment. So burn through is basically burning of base metal due to excessive heat or very slow travel speeds. The weld cracking results in fast weld cooling rates produce a hard, crack susceptible weld microstructure. Fast cooling can be caused by flowing contents inside the piping and the equipment and remove the heat quickly. Electrode considerations. Now we have already talked about that there are various electrodes. We have various ways of identifying electrodes. We have F number, AWS classification, SFA classification. All of those things were given in this code as well, and as well as ASME section 9. So electrode consideration, hot tap and in-service welding operation should be carried out only with a low hydrogen consumable. So it can only be done with low hydrogen consumables. The problem with low hydrogen consumable is that it is very hard to manipulate. So generally a more amount of training is required for the welder. With good training, this can be done. And electrodes such as 7016, 7018, 7048. Extra low hydrogen consumables such as EXXXXH4 should be used for welding carbon steel with a carbon equivalent greater than 0.42%. We have already said that if the carbon equivalent is less than 0.35, it is going to be readily weldable. If it's greater than 0.35 but less than 0.55, then only a preheat is required. If it's greater than 0.55, then both a preheat as well as a post-weld heat treatment both are required. Or where it is potential for hydrogen induced cracking or hydrogen assisted cracking such as cold work piece, high strength and highly constrained areas. Cellulose type electrodes, that is 6010, 6011 and 7010, may be used for root pass and hot passes. However, manipulation of a low hydrogen electrode for root pass is not as easy, but it can be performed by training and practice. It should be noted that the cellulose electrode that have following adverse effects on the integrity of the weldment. So these are the detrimental effects if you use a cellulose based electrodes. So deep penetration, therefore a higher risk of burn through than the low hydrogen electrodes. High diffusible hydrogen, therefore a risk of hydrogen assisted cracking, hydrogen induced cracking, sometimes known as cold cracking. Again, flow rates. So flow rates are basically, we are talking about hot taps. So whenever we are doing flow rates, the liquid inside the piping or the system, what should be the flow rate, or liquid or fluid inside the pipes or the system, what should be the flow rate of those? The appropriate flow rate should be maintained to dissipate the heat from welding, minimizing the possibility of burn through or combustion. the minimum flow rate of 1.3 feet per second for fluids and gases. For liquids, a maximum flow rate is usually required to minimize the risk of high hardness weld zone due to fast cooling rate. The allowable maximum flow rate depends on the process temperature. In general, 4 feet per second is the upper limit. So the minimum flow rate should be 1.3 feet per second, maximum flow rate should be 4 feet per second. This is for liquids. For gases, there is no limit. So there is no restriction for maximum velocity for gas lines. Subject to maintaining preheat temperatures, it is advisable to compensate for heat loss by preheating the weld area to at least 70 degrees Fahrenheit or 20 degrees Celsius and maintaining that preheat until the weld has been completed. Welding on a line under the no flow conditions or intermittent flow condition, example are flare lines, should not be attempted unless it has been confirmed that no explosive or flammable mixture will be generated during the welding operation. In this respect, it should be confirmed that no ingress of oxygen in the line is possible. In cases where this requirement cannot be met, inert gas or nitrogen purging is recommended. Software that takes into account the material properties and flow conditions are often employed to determine if the conditions are safe for in-service welding. Other considerations, so burn through is one of the considerations that we need to take whenever we are doing operations in a refinery or petrochemical plant. To avoid overheating and burn through is basically burning of base metal due to additional heat or excessive heat or very slow travel speeds. To avoid overheating and burn through, the welding procedure specification should be based on the experience in performing the welding operation on a similar piping or equipment. Or it can be based on the heat transfer analysis. Many users establish the procedure detailing the minimum wall thickness that can be hot tapped or welded in service for a given set of conditions such as pressure, temperature and flow rates. Some users include their procedure to use a mock-up weld with actual thickness of the material to be welded less than 6 mm. This means depending on the experience, this can be done. Or you can have a mock-up of the similar conditions, you can weld them. Let's imagine if I have a plate of 6 mm or 7 mm, then I'll have a sample of 6 and 7 mm, and then I can understand if the welding is proper on that sample, then we can understand if the welding is going to be similar in the similar conditions. If the weld is generating burn through in the sample condition, then obviously it will do a burn through in our actual part as well. The mock-up coupon represents the actual material and thickness. The welding parameters are recorded and the weld penetration is verified by HA. This information becomes a supplement to repair package. To minimize the burn through, first weld pass to the equipment or the piping less than 6 mm thick should be made with a 5 mm or smaller diameter welding electrode to limit the heat input. Next is hot taps. We've already said what is a hot tap. So adverse effect can also occur from the heat of the process fluid. In addition, the welding associated with hot taps or in-service welding often cannot be stress relieved and may be susceptible to cracking in certain environments. During the repairs and alteration of the alloy piping material, the material verification of existing and new materials is required to establish the selected components and are specified. Additionally, in some jurisdictions, the hot tap component may be required to have a registered design in which this case should be verified. Buttering the surface of the run pipe prior to attaching the hot tap nozzle is particularly recommended when attaching the nozzle to the pipe fabricated from a plate material to prevent the lamellar tearing of the plate, where the thickness is such that it may occur and result of weld shrinkage stresses. So these are some issues associated with hot tapping or in-service welding for a particular fluids. So if you have acetylene inside the pipe, then if you do hot tapping or in-service welding, then it can result in explosion or unstable reaction. Acetinitrile, acetinitrile, explosion, unstable reaction. Amine caustic, stress corrosion cracking. Butadiene, explosion or unstable reaction. Chlorine, you can have burning of carbon steel. Compressed air, metal burning. Ethylene, exothermic reaction. Ethylene oxide, exothermic reaction. Hydrogen, hydrogen induced cracking or hydrogen assisted cracking. Hydrogen sulfide, that is wet H2S, you can have wet H2S, stress corrosion cracking. hydrofluoric acid, hazardous substance, oxygen, combustion or metal burning. All of these things can happen. So what would be the inspection criteria that an inspector should follow while he is inspecting hot taps or in-service welding? So inspection tasks typically associated with hot tapping or welding on in-service equipment should include the following. Verify the adequate thickness along the length of the proposed welds, typically UT. Verifying the appropriate welding procedure is being employed. Ensure that the welder is properly qualified to use the appropriate welding procedure. Verifying the flow conditions are acceptable for welding. Specifying the sequencing of welding full encirclement sleeves and fittings. Verifying fit up of hot tapping. Auditing the welding to ensure the appropriate welding procedure is being followed. Performing non-destructive examination of the completed weld as well as in-process inspection as appropriate. Typically this includes visual testing or UT shear wave with special procedures for joint configuration, and MT or PT as applicable for the material and temperature. In general, MT using dry color contrast particles will provide required inspection. Witnessing the leak testing of fittings, performing PMI on the hot tap material component, documenting all of the above and having a responsible engineer approve the plan prior to the implementation. Now, we already know that we generally would not prefer GMAW short circuiting method because it can lead to lack of fusion type of discontinuity in thicker materials. It can be a good option if you are using it on a thinner material, but the thicker material will generally have lack of fusion type of discontinuity because the heat input is very low. So due to this inherent nature of the welding process, the BPVC section 9 restricts the process by requiring the welders to qualify the mechanical testing rather than radiographic examination, as LOF can be very difficult to identify with radiography. Limiting the base metal thickness qualified by the procedure to 1.1 times the thickness of the coupon less than 12.7 mm thick as per the variable given in QW403.10. Limiting the deposited metal thickness qualified by the procedure to 1.1 times the deposit thickness for coupons in less than 12.7 mm thick. Making variable QW409 a change from globular spray or pulse spray method welding to short circuiting transmit mode or vice versa an essential variable when qualifying the welder for GMAW-S process. This means if your welder is qualified in globular or spray method, then if you convert it into short circuiting method, then it is considered to be an essential variable and a requalification is needed. This is true for vice versa also. If your welder is qualified for short circuiting method, then for qualifying them for globular spray or pulse spray method, again requalification is needed because this will be considered as an essential variable. So since the transfer mode may be difficult to determine without an oscilloscope, some general characteristics are listed by National Board Classic Bulletin Low Voltage Short Circuiting GMAW from January 1985 to assist the inspector in determining the transfer modes being used. The quick fix characteristics which can lead in lack of fusion type of discontinuity is the reason that this process is frequently specified in purchase requisition. Consequently, a higher standard of non-destructive examination is required in a pipeline welding. Automated ultrasonic testing has been adopted to overcome this problem. So ultrasonic testing is one of the better methods to identify lack of fusion type of discontinuities. The inspector should be aware that the risk of lack of fusion associated with GMAW short circuiting has caused ASME BPVC code section 9 to require welders to be qualified by mechanical testing rather than radiography. Caustic service. Carbon steel and low alloy steels are subjected to stress corrosion cracking in caustic service. Austenitic, that is 300 series of stainless steel, can be very sensitive to caustic corrosion cracking in high temperature steam environments. Although this caustic stress corrosion cracking may be seen visually, the crack detection is best performed with wet fluorescent magnetic particle testing, eddy current, radiography or ACFM. Again, radiography would not be best to identify cracks, but it can be identified if the orientation is good. The surface preparation by grid blasting, high pressurized water blasting and other methods are usually required. The guidelines for when post-weld heat treatment is required for carbon steel may be found in NACE SP 0403 and API 571. So we'll talk about API 571 when we talk about various kinds of damage mechanisms that are subjected to refinery operations. Next is controlled deposition welding. Now we have already talked about what is a controlled deposition welding. Controlled deposition welding is a welding operation where you deposit multiple passes and you don't need to do post-weld heat treatment. It is something like this. So we have talked about this in the earlier video whenever we are talking about the main codes. But let's again look at this once again. So what is an controlled deposition welding? So let's imagine this is your weld joint. So essentially, what is post-weld heat treatment? Post-weld heat treatment is basically heating the weldment until its critical temperature, so that the grain structure can get enough time to revert back to its original condition and your hardness can be lowered down, and to refine the grain structure of the material, and also to relieve residual stresses. But in controlled deposition welding, you will deposit a weldment which is going to relieve the stress of the first pass. Then when you do third pass, it is going to relieve the second pass. Fourth pass is going to relieve the third pass. Fifth pass is going to relieve fourth pass. Sixth pass is going to relieve fifth pass, and the rest can be cut out. So in this case, there is no need for post-weld heat treatment, which is generally going to be very difficult for in-service conditions. So in that case, a controlled deposition welding can be done. Okay. So controlled deposition welding, in some instances, full post-weld heat treatment may have potential adverse effect on the equipment and piping. In those cases, controlled deposition welding may be used in the lieu of post-weld heat treatment, where the post-weld heat treatment is inadvisable or mechanically unnecessary. Depending on the construction code, the use of controlled deposition welding may be required a metallurgical review conducted by the welding or the materials or corrosion engineer prior to the using any alternative, to ensure that the proposed alternative is suitable for the application. Okay. When the reference is made to the materials by the ASME designation, P number and the group number, the requirements of the repair or construction code may apply to applicable materials of the original construction code, either ASME or other, when conforms to the chemical composition and mechanical properties to ASME P number and group number designation. So basically, whatever is written in the original construction code, that has to be followed. So controlled deposition welding is limited to materials from P1 to P3 and P number 4, with further restrictions, that is impact testing and hardness testing in the applicable codes. When the impact testing are required by the construction code applicable to the planned work, a PQR shall include sufficient tests to determine if the toughness of the weld metal and the heat affected zone of the base metal in as welded condition is adequate at the minimum design metal temperature. If special hardness limits are necessary for stress corrosion cracking resistance, the PQR shall include hardness test as well. The WPS shall include supplementary essential variables of ASME section code section 9. Maximum weld heat input for each layer shall not exceed whatever is used in the procedure qualification test. Minimum preheat temperature shall not be less than whatever is written in the procedure. The maximum interpass temperature for welding shall not be greater than whatever is used in the procedure. The preheat temperature shall be checked to ensure that the 4 inches of the material or 4 times the material thickness on each side of the weld joint is maintained at the minimum temperature during the welding. When the weld does not penetrate the full thickness of the material, then the minimum preheat is only required 4 times of the preparation that you have done. So if it's a complete weld, if it's a full penetration joint, in that case, the temperature shall be maintained by 4T or 4 inches, whichever is greater. If the welding is not complete penetration, if it's a partial penetration, then whatever is the depth of your penetration, 4T of that is required, or 4 inch, whichever is greater. When the weld does not penetrate the full thickness of the material, the minimum preheat needs only be maintained at 4 inches or 4 times the depth of the repair weld, whichever is greater on either side of the weld joint. For allowed welding process listed below, use only electrodes and filler metal that are classified by the filler metal specification, with an optional supplemental diffusible hydrogen designator of H8 or lower. When shielding gas are used with the process, the gas shall exhibit a dew point that is no higher than minus 50 degrees Celsius. Surfaces on which welding will be done shall be maintained in a dry condition during the welding and free of rust, mill scale, hydrogen producing contaminants such as oil, grease and other organic materials. Welding techniques shall be controlled deposition welding, temper beading, half beading, all of these things can be done. The specific technique shall be used in the procedure qualification test. So whatever the used in the procedure qualification test, that should be used while making the production joints. For welds made by SMAW after the completion of welding and without allowing the weldment to cool below the minimum preheat temperature, the temperature of the weldment shall be raised to a temperature of 50 degrees Fahrenheit plus minus 50 degrees Fahrenheit for a minimum period of 2 hours to assist in outgassing diffusion of any weld metal hydrogen picked up during the welding process. After the finished repair welding is cooled, the final temper bead reinforcement layer shall be removed, leaving the weld substantially flush with the surface of the base metal. So the additional weld that you have done should be cut and the weld should be generally flush with the base metal. In general, controlled deposition welding is not usually applied to the situation where the reason of post-weld heat treatment is to avoid stress corrosion cracking. So it can be used, but when the post-weld heat treatment is required for stress corrosion cracking, it is generally not recommended. Welding processes for controlled deposition welding are limited to SMAW, GMAW and GTAW. For controlled deposition welding in pipe, flux core arc welding process may also be employed, with a specific WPS developed and qualified for each application. If the original material specification is obsolete, the test material used should conform as much as possible with the materials used for construction, but in no case shall be of a lower strength or carbon content above 0.35%. So if the original material is available, use the original material. If the original material is not available, then you can use a material that is closely related to the base metal, but in no case it should have lower strength or carbon content greater than 0.35%. Finally, the section 12, this is the last section for APF 577, is safety precautions. Inspector should be aware of the hazards associated with welding and take appropriate steps to prevent injury while performing the inspection task. As a minimum, the safety rules and regulations should be reviewed as applicable to the welding operations, which is given in Annex G. Okay, so this was all for APF 577. Let's look at the annexes that are given. So Annex A is terminologies that are used in weldments. So different types of terminologies, what is a joint, what is a welding symbol, what are types of grooves can be made, what are some types of welding that can be done, what are some types of surface finishes that you can have, that is concave, convex and flat positions. This is a welding symbol. So whatever is written on the bottom side is going to be the arrow side, whatever is written on the top side is going to be on the other side. So this is what is written on the SMAW electrodes. The first two letters will determine strength, third letter will determine position, and the final letter will determine the coating characteristics. This is for GMAW or GTAW. So the first two is going to be electrode, the next two are going to be strength, this is going to be the solid wire, and the final is going to be the chemical composition of the filler metal. This is flux core arc welding, again the same thing. Electrode, this letter would represent strength, this would recommend position, this would recommend again a position, and this would recommend the chemical composition and operating characteristics. Action to address improperly made weld. So if you have an improperly made weld, what should an inspector do? So when the production weld made by a non-qualified welder or improper welding procedure should be avoided to ensure that final weldments meet the code specification or user requirements. A welder may be unqualified for several reasons, including expiration qualification, not qualifying the welding process, thickness not qualified in the technique, or not qualified for materials for construction. Okay, so whenever things like this arise, whenever in the production weld you are seeing any kind of discontinuity and the welder is not qualified, in that case the repair weld shall be made by the qualified welder. So this is the flowchart that is given. So identify and quarantine all the weldments made by the welder. Test the welder. If he passes, consider non-destructive examination and accept and document the welds. If he fails, then apply the retest criteria, test the welder. If he passes, then again it goes there. If it fails, then cut out the weldments and provide and do the weldment with the help of any of the qualified welders that you have. The same thing. This flowchart is going to understand this flowchart is going to help the inspector if the welds that are made is not the problem of the welder, but it is the problem of the welding procedure specification that you are using. So review the requirements. If the requirements fail, then cut out and re-weld with the correct WPS and PQR. You can hold it, then determine the properties of the WPS and PQR, review or rerun the PQR. If it's unsuitable for application, cut out. If it's suitable for application, repair the weld and complete the non-destructive examination. If it fails, then review the non-destructive examination, pass and accept the documents and the welds. So this is the recommendation that is given for the inspector. And WPS and PQR review, this is going to be the important parameter for the API ICP examination, because the inspector job is not to make the WPS and PQR. It is to review that whatever the WPS and PQR are made, are they as per the specification? Are all the essential variable, non-essential variable and supplementary variables are present there? Okay. So the following exhibits are used to guide for validating the welding procedure specification and procedure qualification record for process covered in API 577. It is not intended to be used for development of WPS and PQR. It is just for verifying the WPS and PQR. For creating these documents, greater detail is needed and should be accomplished by the qualified personnel utilizing the respective construction code or specification. It is further recognized that owner user may have specific requirement that exceeds the requirement of a code or specification. Examples include additional hardness testing, minimum preheat temperatures, or limit on heat input. While such additional requirements are not necessarily required by the code and specification, such welding procedure will need to meet the additional requirements for compliance. API Recommended Practice 577 only considers ASME boiler and pressure vessel code section 9 because it is generally used for development basis for the fabrication and repair of piping and pressure equipments. Other codes and standard may have similar variables or may vary greatly from ASME section 9 requirements. Variables, obviously we already know this, that we have essential variable, supplementary essential variable and some non-essential variable. Essential variable, change anything in essential variable, a requalification is needed. Supplementary essential variable will be considered like an essential variable if a toughness requirement is done. So whenever you change anything in the supplementary essential variable, a requalification is needed and a toughness test or impact test is also needed. Non-essential variable, change anything in a non-essential variable, don't need to consider them or no need for requalification because they are not going to affect the mechanical properties of the weldment. Document verification, annex utilization, color code for WPS and PQR. Red is going to be essential variable here, yellow is going to be non-essential variable and green is going to be supplementary essential variable. So this is an example of a WPS. And this is an example of PQR. Okay. For different processes, you'll have different essential and non-essential variables. So all of these things are given here. Next is guide to common filler metal selection. Carbon steel, you can use these. Same thing for SMAW, copper and nickel based alloys, low filler metal designations, low alloy filler metal designations, examples of radiographic reports, inspection considerations. So inspection, these things are to be inspected by the inspector. Building safety, and that's it for this document. So in this video series we have seen what are some codes that are used in welding operations. So we have seen section 9, we have seen API 577. This video series was generally recommended for API ICP examinations, but it can also be used for various other applications also. It would not be good for structural welding because in structural welding we would be using a different code, that is AWS D1.1 or something like that. But this will be generally good for pressure retaining equipments, and this should be reviewed because most of the questions or a good chunk of question, that is almost 20% of the questions, would be arising from the welding operations in your AP ICP examination. That's it for this video. In the next series, we'll be looking at some other aspects of AP ICP examination. Thank you.